All right, hello everyone. Welcome back to Historical Geology 1404. Today is lecture 2. We are still in our physical geology review period with a few other extra fun things thrown in. First of all, start off with some announcements. What announcements do I have? You're getting lectures 2 and 3 this week, which means next week you will get lecture 4 and exam 1. Okay. You're getting your first lab today, and your second lab next week on Monday. Let's see what else. Announcements. Can't think of any other announcements. Oh, I think I mentioned this last week. I'm doing the America's Favorite Teacher competition this year. I sent y'all out a voting link. If you don't mind voting, I'd appreciate it. I don't know what my chances of winning are. Currently, I'm 5th out of 80-something people. So I'm pretty high up there. But I'm also not going to be that guy that does things that I wouldn't normally do to try and win. It doesn't go through Facebook. It's not a Facebook thing, but they use Facebook to make sure you're not an AI. Yeah, because right now people still need to, my understanding of it is people still need to make an account in person first, and then they can like turn it over for an AI to use. But it's their way of making sure that you are a person voting and not someone using an AI to spam a Facebook account votes. Okay? So yes, you do need a Facebook to vote. If you don't, I'm not asking you to make a Facebook to vote. Like I said, I'm not getting up in everyone's faces to try and make this happen. If it happens, then it's great. But if it's going to happen, it's going to happen on my terms, being who I am, and not making a nuisance of myself. But yeah, I'd appreciate whatever votes you can send my way. Voting can happen daily. You can do it every day if you feel so inclined. I can't offer you extra credit to do it. That's not ethical because it's purely only for my benefit. Even though actually technically Bill Nye the Science Guy would come and visit Odessa College. So there's that cool, but it's a personal thing. So I can't offer extra credit for that, nor would I. All right, I can't think of any other announcement style sort of things. Can you guys, anything we need to talk about? Any interesting stories that you may have heard of over the weekend? No? After a couple of unsuccessful tests, the Artemis rocket is being rolled back out to the launch pad. Yeah, they're getting ready for another attempt to launch it. So they'll be running the exact same tests once they get there. And this is where it failed last time, was they did all the tests at the docking station, and then it passed, and then they rolled it out to the launch pad, and it failed one test there, a fuel pump test. And they had to roll it back to the docking station and go through all of the tests, take everything apart and fix it and shine it and oil it and put it all back together, right? And then they're rolling it back out there now, and they're going to run the same tests again. Anytime you move something that complicated, you got to test it, especially when human lives are on the line. So, bless you. Fingers crossed it passes everything this time, and we can make history by sending some astronauts further from Earth than they've ever gone before. Oh, here's another cool thing before we get started. I think I mentioned that to you guys that next year I am doing this big 50-year anniversary of the launch of the Voyager spacecraft activity for the public, right? It's going to be like a space science education day focused around the launch of the Voyager spacecraft. Well, I was just out of curiosity, I did some math. I think it was back on Thursday or Friday, and I found out that Voyager 1 will reach 1 light day from Earth on my birthday this year. How serendipitous is that? Like, here I am getting ready to celebrate Voyager next year, and it It returns the favor by reaching one light day on my birthday. It's pretty special to me. Happy birthday to me. That's going to be in November, so it's a ways away, but, you know, at that point it will happen. Okay. Nothing else we want to talk about before we get started today? Any questions from last week? No? No questions about how the class is going to go? We're all pretty familiar with the way that Professor Hart teaches now. Old hat. Everyone's good. If it's green, it's not locked on me, I think. So I need to make it blue. Yeah, blue is locked on me. Great. All right. Come on in. Alrighty, well, let's jump on in. So I gave you a brief rundown on the rock cycle last week. This is just a different way of showing it to you. Rock cycles for basic courses most commonly are shown in that kind of wheel diagram, right? The circle with kind of the spokes that go towards the middle, kind of like a bicycle wheel, right? That kind of crisscross and show you where things can go and where they can't go. There are exceptions to some of those rules, right? Well, this is another way of looking at your rock cycle. This one is far more inclusive of all of the different components that we've learned about, except it's a little more confusing because it's not really a wheel. It's all still a cycle, and these things still tie into each other here. It's just a different way of portraying it. Might be useful if you're willing to break out of that circular cycle visual that I showed you. This might be a useful thing to hold on to for reference later on in the course if you so desire, because it does give you a little bit more visuals in terms of what each step represents and what happens along the way. Okay? But this is the one that I showed you before. Okay? And since we rehashed that last week, I don't really need to rehash it now. Just a couple of different ways of showing it to you. Okay, so what is matter? Anything? Liquid, solids, and gases are states of matter. Yeah, which, by the way, there's a fourth. Did you know there's a fourth one? Yeah, plasma. Huh? Something we have? Matter is something we have. Does that mean something you possess or just something that's around? Around, yeah. Okay. This is kind of a very, it's kind of a vague question. What is matter? Well, nothing. What's the matter with you, right? That's the right answer. But yeah, you're actually hitting it right on the head, pretty much, Jasmine and Sergio. And between you guys, you're hitting this whole thing. Whoa, what? Serge, I'm so sorry. Oh. All right, great way to start. Okay, so Sergio will take the credit. He won't mind. Okay, so where was I? Oh, matter. Okay, so solids, liquids, and gases, right? But what is in those states of matter? What is in solids, liquids, and gases? What's maybe another word that we can use to describe? Molecules. Okay, I like where this is going. Molecules are made out of? There it is. Okay, atoms. Okay, matter is things, right? And those are made out of atoms. Okay, and those atoms are elements. An atom is a single unit of any given element, right? So, based on what you remember from 1403, what is an atom then? Or chemistry, taking chemistry. It doesn't have to be for my first class. What is an atom made out of? Building block of everything around us. What is a building block?
Something you build with the block.
Yeah, okay. A blueprint is more like a plan. This raises some very interesting philosophical debates there as to physics, which we won't dive into right now for the sake of time. But if you think of atoms as building blocks, like Legos, right? Like Legos. You guys ever play with like Lincoln Logs? No? You never played Lincoln Logs?
They have like indentation.
Yeah. Like they interlock with each other, and you can make like log cabins. They call them Lincoln Logs because it like makes like an Abraham Lincoln log cabin out of them. That's what they were for. You can make other stuff with them, but limited. Legos, much better example. You can make Legos into any shape you want. You know what my favorite thing to do as a kid was? I loved to buy Lego sets and build the thing that they were for once, and then like immediately take them apart to make whatever I wanted. I felt obligated to make whatever the set was for first, though. Like if it was a Harry Potter set, I'd make it, be like, oh, that's cool. And then I'd take it apart and build a bunch of spaceships.
Have you seen on like social media that people will buy whatever Lego set and they'll just build the Millennium Falcon?
The what? Build a Millennium Falcon out of any set? That is hilarious, and I have not heard of that. That's great. I did see, you guys ever watch Stranger Things? Okay, so I saw that there was this this Lego set of the Upside Down, where you build it, and it's got like 2 pillars for support here, and then there's a set that goes on top that shows Hawkins, the town, and then a set that you build on the bottom from the bottom of the shelf downward. That's the exact version of what's on the top, but in the Upside Down, and it's all dark and gloomy and stuff. I thought that was really cool, really inventive, kind of looking at it in the inverse kind of perspective like that for a Lego set. But yeah, no, I would build the thing, and then I would build a bunch of spaceships out of it. I ended up with a lot of Lego spaceships as a kid. But yes, if you think of each Lego as an individual atom, and then you can interlock those together, and you build a larger structure out of it, right? With some geometric shape, okay? Now, those atoms are made out of things. They are made out of 3 smaller particles. What are those particles? Protons, neutrons, and electrons. Exactly. What do we remember about protons? What are the properties? So when you say they're positive, what do you mean they're positive? Like they're absolutely sure about something?
Like they're positively charged.
They're positively charged. Right, exactly. Okay. So protons have a positive charge. Sure. Okay. All right. What else? They dictate what? What were you saying? You were pointing over here.
The amount of valence electrons.
They don't determine the number of valence electrons. They determine something else. They're part of the mass.
Protons.
What do we call that? The atomic number. The atomic number is the number of protons in the nucleus. The combined mass of the nucleus is what makes the mass, but it is the atomic number that's determined by the number of protons. Yeah, the columns, exactly. Yeah, we'll get there when we talk about electrons, exactly. But for now, protons, the number of protons that your atom has in its nucleus determines which atom it is, which element it is, I should say. Okay? Great. Okay, neutrons. What's a neutron? What does it mean to be neutrally charged? If it's neutral, does it have a charge? We start getting into the real deep chemistry here. It may or may not have a positive and negative charge at any given time, but we're going to treat it as if it has 0 charge whatsoever. What were you saying? Okay, why would the number of neutrons determine isotopes? Where do neutrons live in my atom? In the nucleus, right? That's what we call it. Yeah, the middle. You were absolutely right. You were absolutely right, and I appreciate that. But in science, we got to use the words, right? Okay, so it's in the middle. It's in the nucleus. That nucleus, protons and neutrons together, combined, make the mass. And it is the mass, or changes in that mass, that determine whether or not you get an isotope. Yes. Okay. This mass is the combined atomic mass of all of the particles, including the electrons, technically. But those are extremely tiny. About 1/2000th the mass of a proton. Which, speaking of electrons, what is an electron? They are particles that orbit a nucleus. Yes. What else do we know about them? They are negatively charged. Protons are positively charged. Neutrons are not charged. Electrons are negatively charged, which means that at some point, you're going to end up with a balance, right? You're going to have a balance of charge between your protons and your electrons, or an imbalance. What do we call it when there is an imbalance of charge in my atom? An ion. So you can have either a positively charged ion or a negatively charged ion. What would make something have a positive charge? Less electrons than the protons. What about a negatively charged atom? More electrons than protons. Exactly. There you go. Okay, so, and then with ions, positively charged and negatively charged are often attracted to each other, like magnets. That's exactly how magnets work. You get an electromagnetic field, right, as a result of this happening, and then they're pulled towards each other. Electromagnetism is an extremely powerful force. You guys remember I told you last time about the 4 forces? You remember what those were? Gravity is one. Well, okay. We're learning more and more about gravity every year. Is it actually a force, or is it the fabric of space-time? I don't know. Yes, we could spend hours on this, but that's something we'll leave up to quantum physicists, right? But yeah, gravity for now, we treat that as one. What's another? Well, that's an aspect of it. Strong nuclear and weak nuclear force are 2 of the others. And then electromagnetic force is the 4th. Do you know what the weakest force is? It's gravity. You know how I know it's gravity? Because I can pick this up. The entire gravitational force of our planet is trying to keep me from picking this up, and I can win. That's how I know gravity is the weakest one. Okay? Electromagnetism is the next weakest one, by the way, and that's about 42 times more powerful than the force of gravity. Okay? Extremely powerful. That's what makes magnets work. That's why when you make an electromagnet, it's impossible to pry that thing off of stuff. Like high security doors, like what you get at the Pentagon and stuff, are electromagnet. Because all you need to do is run a small electrical charge through those magnets, and you'll never rip those things apart. You would have to carve through the door to get through that thing. Yeah? The what? Oh, the high-speed trains. Yeah, bullet trains. Yeah, use electromagnets. That's why they can zoom away at 100 miles an hour on this tiny little rail 100 feet over the ground, and they are safe. Because through the city, like if you see these things in Asia, they are insane, okay? Absolutely hauling through the city at 100 miles an hour and stop for the next stop, pick up right again with the new passengers. Electromagnets, very, very powerful force. Great. Okay, so here we have an example of an atom. Now this atom has a certain number of protons and a certain number of neutrons in the nucleus. It has a certain number of electrons in its orbits. I mentioned this last time. Most atoms, most elements, actually have more than one electron orbit. Okay? This one, however, on its outermost orbit has 1, 2, 3, 4. What do we call the outermost orbit? The valence shell, yeah, and the electrons that occupy it, valence electrons. How do I know the location of this atom on the periodic table based on the number of electrons? This is what you were mentioning earlier. Yeah, the columns on our periodic table of elements. We organize these by a certain number of properties, one of which is the number of electrons in the outermost orbit. So this first column here has 1 valence electron. The second column, 2 valence electrons. We skip over these because they share electrons very freely with themselves, and so it kind of breaks the rules of why we organize them into columns in the first place. But then we have over here column 3, 4, 5, 6, 7, 8. These ones in column 8 are special. Why? They're balanced. What do you mean they're balanced? 8 valence electrons. So why would that matter? Is there a rule? Yeah, good, good. Okay, the octet rule. Okay, the octet rule states that atoms tend to gain, lose, or share electrons until they possess 8 electrons in the outermost shell. Why 8? Don't know. Law of the universe. It just is what it is. Okay? But these ones already have 8. Radon, xenon, krypton, argon, neon, helium. We call these noble gases. Because they are not actively seeking to bond with anything, we use these for very special purposes. We store volatile things in them. Things that are actively seeking to bond with other stuff, and especially the ones that have a violent reaction when they do so, like an explosion, we tend to keep immersed in those gases, those noble gases. Why? Well, yeah. Well, because they won't blow up with each other, right? I keep something immersed in argon or radon, right? Or xenon, and whatever is in that is not going to react to anything else as long as it's purely just that noble gas. Okay, great. So what we have here is, how many does it have, this example? How many does it have in its outermost shell? 4. So which column is it in? 4th column? Which atom is it? How do you know?
Because it has only two orbit shells, so it'll be the first 2, then it's the 4, so it's 6. I think that's the atomic number.
But you don't determine atomic number by the number of electrons. Atomic number is determined by something else. The number of protons. How many protons are in that nucleus? 6. So you are right. This is that first one because it has that number of protons, not the total number of electrons, though. What element is that? Carbon. What do we know about carbon? Is carbon kind of important? Yeah, carbon is kind of important. We like carbon. Why? It's essential for life as we know it, right? To make this, you need carbon, as far as we know. As far as we know, this is true. There is the potential for other things. Why? Because carbon has a certain number of valence electrons. It'll bond to certain things. The next one down, what is it? Silicon. How many valence electrons does that one have? 4. So turns out silicon and carbon are capable of bonding with a lot of the same stuff. But carbon bonds preferentially. It's just easier to bond with carbon for one reason or another. So in science fiction, that's a very good question. They have different masses. That's part of it. Okay? Silicon has more mass. They both atoms are approximately the same size. Man, my camera keeps losing track of me here. Both atoms are approximately, come on, stay with me. Over here. Hi, over here. New camera, learning the rules. Hold on. Both atoms are approximately the same size and have the same charge, which means that they can hold bonds in approximately the same ways. There we go. All right. Oh, and it's zoomed in on me too. Let's zoom out. There we go. More. More. Come on. Zoom out. Out. Hello. That's probably confused by the picture. All right. That might be as good as it gets for zooming out right now. Let's try now. Nope. That is what it is. All right. So science fiction, theorizes a lot or makes stories a lot about things like silicon-based life. What this essentially would mean is not a biological organism like you and me. It would be a mineralogical organism. Why? Because what's the basis of all silicate minerals? Silicon tetrahedron. Silicon and oxygen. Carbon and oxygen in combination with hydrogen makes carbon or organic compounds. And those organic compounds make life as we have it. You supplement out the carbon and you swap in silicon, and you could conceivably have silicon-based life. Not something that we can replicate here because we have a lot of carbon here. And here on Earth, because carbon is easier to bond with, that happens. But what about on a world with very little carbon but a heck of a lot of silicon? Don't know. Really cool to think about though, right? Huh? Probably out there. I mean, do you guys remember what was the number of planets that we estimate are in the universe? Do you remember that from last term? Or 70 quintillion planets? And even if life only exists in one of a billion of those, that's still 700 billion planets with life in the universe. And how many of them have life just like ours? Probably not many, but they probably all have life of some kind. Okay, so here we have our carbon. Now, we already kind of talked about this. Let's talk about valence shells and all of that, and all the different variations of that. I'll come back to this idea about carbon in a second. I'm going to show you some more. How do you what, iron?
How do you like distinguish iron?
Distinguish it from what, though?
Like other atoms.
Like if I were looking at a metal, how would I figure out if it was iron?
Like how would you figure out it's metal?
Versus other metals?
Versus other regular, or not regular, but other.
Oh, okay. So is the basis of your question asking how I would pick one atom out from a bunch of others?
Yeah, I guess.
Okay. So there's a couple ways you can do that. You can use X-ray fluorescence, okay, which is basically you bombard something with X-rays, and all atoms will interact with X-rays in a different manner. And so what it will return is different energy spikes at you as it's being bombarded by X-rays, okay? I used an X-ray fluorescence machine on this meteorite over Christmas break. I think I told you guys about this. But basically what I did was I bombarded this with X-rays in this machine, and it returned different energy spikes to me in the form of a spreadsheet, which I could then interpret as, well, we know through prior testing that this energy spike corresponds with iron, this one mercury, this one magnesium, right? All the different metals in here, all the different elements will respond to X-rays in different way and return different energy spikes at different wavelengths and frequencies and the such. So we can then read a document like that and say it is this much of this metal, this much of that metal, so on and so forth, right? Now, that works really well if you have an object in your hand, right? And you can test it like this. But what about something that's millions or billions or trillions of miles away? How can I tell if a star has iron in it?
Can't remember how to say spectron.
You've got most of the word right there. Spectroscopy. Same sort of principle here. Different materials will send off different wavelengths of light when they are energized. Okay? I wish I had an example of this. If I was teaching physics and only physics, I would have invested in this already. But you can get different lamps that have different vacuum sealed chambers in them filled with different gases. So I can get one filled with nitrogen. I can get one filled with oxygen. I can get one filled with carbon dioxide, right? I can fill different things. And then you put high energy light through them, they will be different colors. Nitrogen will be a different color, and all of these different elements will show off different colors even though you're putting white light into them. Why is that? Because of the wavelengths of light they are putting off. So this is an example of spectroscopy. I can look at a star 60 million light years away and know what elements it is burning for fuel right now. What does it have in it by the wavelengths of light I am bringing in. Do you have a comment?
They also do that with like nebulas and stuff.
Yes.
Like the very famous picture.
Yes.
The pillars of creation stuff.
Yeah, exactly.
It's just dependent upon what elements they take of space.
Absolutely. Anything that emanates light, you can use spectroscopy on to figure out what elements were involved in making that light in the first place.
So like in the different colors of burning fires, right?
Yeah, exactly. So why does fire turn green? It's burning something that puts off a green wavelength. Well, that's not exactly true. That's more like a gas that it's expelling. Green is very interesting in nature. The number of elements that give off a green wavelength of light are very rare. I can't think of one off the top of my head. Not one that would occur in a star anyway. Because there are blue stars, there are red stars, there are brown stars, there are white stars, there's orange stars, there's all sorts of stars, but there are no green stars. None of the elements that occur naturally in a star actually put off a green wavelength.
What about the northern lights?
The northern lights exist because what's happening is we're getting a whole bunch of solar radiation that's constantly slamming into our Earth's electromagnetic field. Most of that stuff bounces off and around. When it happens at either poles, because you can get northern and southern lights, right? When that happens, it's the gases up at the top of our atmosphere up there are getting slammed with all of that radiation, and they're getting ionized. Okay, so you're seeing ionized particles interacting with our upper atmosphere and kind of skipping over our electromagnetic field. Okay, so that's why it makes that kind of beautiful, ripply, multicolored rainbow that you're seeing there. You're literally seeing radiation interacting with our electromagnetic field. Yeah, very beautiful.
Isn't that like with the purple hue that we have here? Like with that pollution?
Okay, yeah, well, pollution is a whole nother thing.
No, yeah, but like.
Yeah, pollution will diffuse wavelengths of light, which is why if you ever go to a big city like London or Salt Lake City, well, you'll see atmospheric pollution diffusing wavelengths of light. Yeah, it's diffusing the light. Now, light pollution is another thing. Do you guys know that light can cause pollution?
Yes.
Why? Light is radiation. It is particles, photons specifically, okay? So when you send a light in any direction, it is only traveling at the speed of light, right? That's the upper limit, right? Which means that if I'm looking at something hundreds of millions of light years away, and all of the light that we have blasted into space in that direction, I have to look through that to see what I'm trying to capture an image of. So the more light that we blast up into space, the harder it is for us to see what's in our neighborhood, basically. Okay? The first radio signals ever sent by humanity in the 1800s? When was the first radio signal? I don't remember. Can someone look that up for me? They're still traveling through space at, guess what? The speed of light. Right? They're still going on. They're still going out there. The silly little messages that me and my brother, sent to each other on radio walkie-talkies when I was a kid, they're out there somewhere, assuming they made it through the atmosphere, right? So that's light pollution. It makes it difficult to see the light coming towards us because it's getting diffused by the light that we have emanated ourselves. Okay? Also, in the short term, when you're standing like in the middle of the city, you can't really see the stars because there's street lights around you. That's more of our close-to-home example of light pollution, right? You have to go way out into the desert to see a beautiful night sky, right? This is part of the reason why we've actually put our more powerful telescopes slowly further and further away from the Earth, like the James Webb Space Telescope that we just put out there that's returning all those gorgeous images to us, further from Earth than any of our telescopes have been. Okay, trying to avoid more of that light pollution. Huh?
Isn't it actually orbiting the sun? It's not orbiting Earth itself.
It's on its way out still, I believe. But the main objective is that it does have a heliocentric orbit, not an Earth-centric orbit. Yeah. Wow, we kind of went way off topic here, but I loved this conversation. You guys have fantastic questions. Anything else you want to ask while we're on this? Yeah? No? Okay. Electrons. We talked about electrons already. Talked about the octet rule. Jasmine brought that up. We didn't need to mention that anymore. Electron orbitals, right? We talked about electron orbitals. Okay, we're coming back to carbon. We're coming back to carbon. Carbon, aside from the unique things we've already talked about, being essential for life as we live it, right? There's a few other cool things. Carbon will bond in a couple of different ways. Carbon will bond in a kind of loosey-goosey 3D framework that's much easier to move and mold and shape. Very loose framework. And when it does that, it makes a mineral we call graphite. You're familiar with graphite, right? How many of you have pencils right now? Yeah, graphite. Graphite is a mineral in your pencil lead. It is so soft, you can literally write on paper with it. Okay? That's one way that carbon will bond together. Another way is a dense cubic framework. And this makes diamond. This is what the molecular structure of diamond looks like. Okay? So remembering that carbon has how many valence electrons? 4. Each carbon with 4 valence electrons is going to bond with another carbon at each of its corners. So this carbon is bonded here, 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 and here to those other 4, each of which is donating 1 to this guy. So how many does it have in total now? 2, 2, 2, 2, 8. It has all 8 it wants. So when you take carbon and you bond them in this way, you make this cubic framework. Every single carbon is so tightly woven together, bonded together in such a satisfying manner, it is very difficult to break them apart. And that is why diamond is so hard. Now, there's this really cool thing. What is the name? It was theoretical at first, but there is another way that you can bond carbon molecules together and make diamond in a different way. And it was only theoretical until someone figured out that it happens naturally in high impact energy meteorites. No, coal is high in carbon because the trees and other plants that make that coal were high in carbon because they were organic. Okay, it's a concentration of that. What happens here is a carbon-rich meteorite or asteroid on its way through the atmosphere gets superheated, and then the impact pressure of slamming into the Earth makes it bond. Like the high energy and pressure forces it into a whole new structure. And it's a way of making diamond that we have not seen occur naturally here on Earth. And it was only, like I said, hypothetical. This might happen in certain cases. And then only a few years ago, someone actually found a sample of an asteroid with a piece of that in it. Like, hey, this happened. And then I read a story, I want to say it was a week or 2 ago. I didn't even read the whole story. I was waiting for something. I had an appointment for something. I was scrolling through. I was like, whoa, this is really cool. I didn't even finish the story. I forgot about it until just now. But they've replicated it in a lab, I think, where they forced diamond to form in this totally new structure, which is pretty sick. When you can take things in the natural world and replicate it in a lab, it is super cool. At least in this guy's opinion. All right. So that's how carbon makes atoms, or makes diamonds. Hello. Ruh-roh, Raggy. Don't do it to me. Okay. All right. All right. So that's what happens when you change your electrons. You'll end up with an ion. Those ions bond together. They make strong bonds according to the octet rule. Okay. So Then when you change the number of neutrons, you change the mass. That will make my atom fit into one of two categories, stable or unstable, right? We've talked about stability as a concept in nature before, right? Why is stability such a fundamental concept, an important concept in what we've talked about? Huh? Okay, so you're talking about an example of the ways that nature can change to remain stable, but why stability? Yeah, why is everything trying to reach stability? This is taking the concept at a deeper level. Everything changing is kind of an example of the opposite effect. Do you guys know what the second law of thermodynamics is? Entropy. Do you know what entropy is? Ever heard of this concept?
Isn't it something about movement or like? I know it has to do with movement, doesn't it?
All things in our universe are constantly moving, I suppose you could say, towards a state of disorderliness. Things fall apart. Now, for me to explain this concept to you, and for you to understand it, I'll put it in a very basic perspective. Do you remember how I told you we believe the universe started? How did it start? What was that event called? The Big Bang, right? The Big Bang, all matter in the universe was somehow stuck into an area the size of the head of a pin, and then it exploded outward. Well, the moment of that explosion, that first picosecond, we're talking about all of that matter compressed into this tiny little area. The temperatures would have been estimated in the millions of degrees, okay? And as it expanded outward, kept expanding, blindingly fast, speed of light, right? Explosively outward, as all of that matter is occupying more and more space and interacting with all of the other matter less, what's going to happen to my temperature? It's going to go down. As all this matter has more room to occupy and less interaction with each other, temperature slowly starts to decrease. Okay? The universe has been expanding for about 13.7 billion years, at least. Right? We talked about this last time. Right? We don't know exactly how large our universe is, but it's been going for at least 13.7 billion years because that's the oldest light that we've absorbed by our detectors. Okay? Over all that time, the temperature of the universe, has it been going up or down? Down, because all this matter, relatively speaking, is getting further and further apart, right? Which means that eventually, what's the future ultimate end of our universe going to be? Oh, we don't know yet. That's one hypothesis, that it expands to a point where it'll rubber band in on itself and collapse. That depends on how space-time works, right? But what we do know is it is continuing to advance outward, continually expanding, which means that the overall temperature of the universe is continuing to decrease. Eventually, according to that trend line, we will reach a point where all the matter in the universe is so far apart from itself that there is no energy making heat. Our universe will not die in heat. It will die by freezing to death. Okay? According to that trend line. So this is an example of what I'm talking about with entropy. Increasing disorderliness. The larger our universe gets, the less celestial bodies are formed inside of itself. Okay? As time goes on, things either maintain their state of stability or generally degrade that stability. But in general, all things in nature seek that state of stability. It's almost like the second law of thermodynamics, which we observe as entropy, is actively being fought against by the parts of nature that are inside of it. It's very interesting to observe things like that. This kind of, that alone in itself is some sort of balance. Okay? The fight between entropy and stability in our universe. Okay? We're waxing very philosophical today. Okay. So, but you change the number of neutrons in your atom, and that changes it into an isotope. That isotope is either going to be stable or unstable, okay? Stable ones, they don't mind so much. Sure, you gave me an extra neutron. What's a neutron between friends, right? They don't give a they don't care, okay? And then you add a few more, or you take a few more, and then they start actually minding, okay? Then they actually start to care, okay? They're going to become unstable. What does that mean? Well, when an isotope reaches a state of instability, it is going to blast particles off of itself until it reaches that new stable condition. We talked about this last week when we learned about radiometric dating, right? I don't need to belabor this point too much. Radiometric dating is we know how long it takes for them to go from an unstable isotope to a new stable atom, and we can measure the age of something by how many of those half-lives have passed. Well, we have other ways of using that, right? Familiar with this particular method. This is one that our world is constantly in fear of these days, right? Nuclear weapons, this is how they work. Instead of letting all that energy get released over that period of a half-life, you essentially force a reaction that causes all that energy to be released at once. You guys are familiar with the first and only nuclear weapons to ever be used in violence? What were those? There were only two ever used this way. At Hiroshima and Nagasaki. Fat Man and Little Boy, those were the names of the bombs that were dropped there. Okay? Killed a lot of people. I think I probably told you the story. I lived in Japan as a kid, right? And I went and I visited both blast sites and visited the museums that are there. It's very sobering. There's a reason why they've never ever been used again. The world came together and said, yeah, we can't ever let that happen again. Even the United States, who dropped it because the Japanese Empire had wreaked so much devastation on the United States and their allies, they're like, we never want to have to do that again. It was truly awful, guys. Lots of death, lots of destruction, people melting in the streets. Not something that you ever want to see in your city or in your country. But the bomb that they built to do that devastation, the two bombs, they had dozens of kilograms of uranium in there, an unstable isotope of uranium. Dozens of kilograms of it. Only 0.01% of that mass actually blew up. They had enough uranium in those bombs to light up the entire nation of Japan. But again, this was the first bomb actually tested in violence. The first actual effective field test of a nuclear weapon. They didn't have the tech down just right. These days, if you put that much uranium in a bomb, you annihilate a nation. Okay? Only less than 1% of the uranium in those bombs actually went up. And it still did that kind of devastation. Okay? That's the power that you have in these nuclear forces. Okay? Now we can take that potential energy and turn it into actual kinetic energy in another way. Nuclear reactors. Okay? So instead of taking that uranium and turning it into a bomb, you take that uranium and you harness the natural radiation coming off of it to create heat. That heat, in turn, creates steam out of the water you put nearby. That steam turns a turbine and makes electricity, just like a coal power plant or an oil power plant would do. Okay? Or water on a water mill, or a wind on a windmill. They all turn a turbine, which causes two magnets to interact with each other. Those magnets, each with their own electromagnetic field, starts to overcharge some electrons, and those electrons can get transferred through a wire and make electricity, okay? Nuclear reactors do the same thing using naturally occurring radioactive isotopes, okay? That's the philosophy behind those. Still not perfectly clean, but it's pretty good. It's pretty good.
How long do you think it'll be until we're using nuclear energy in a good percentage?
That's an excellent question. We could do it right now, but the problem is the public doesn't trust it yet. That's really the only problem. Our
They blame like Chernobyl and stuff like that, right?
Chernobyl, 3 Mile Island, Fukushima, right? It doesn't take human error to make a nuclear incident. There are things which, whether or not you believe in God or not, there are literally legal terms for things like natural disasters called acts of God. Okay? It's in our legal charter. We call them acts of God. Things you cannot control. Things that were inevitable, things outside of human control or influence to stop, that can occur. Like the Fukushima earthquake in Japan, which caused that nuclear reactor to breach and a whole bunch of radiation to go into all the nearby rice fields that irradiated a whole bunch of rice, irradiated a whole bunch of fish. There were radioactive fish washing up on the coast of California, okay, from this thing that happened in Japan. You cannot stop things like that. You can only try and prepare for them, okay? And it's things like that that really make the public leery about nuclear reactors because there's a whole lot of damage that can come from something like that. We are moving on into what they are calling fourth generation reactors though, okay? Which essentially are smaller, more compact, portable to an extent, and a lot easier to shut down, a lot easier to contain if there's a breach, but they are not widespread. The technology is not widespread yet. They're hoping that in the 2030s, this technology really catches on, they can build more of these things out there, get the public to start to trust them, so that over the next 20, 30 years, we can start implementing them more. We may be entering the next nuclear age. I really hope so for nuclear power, because honestly, that's the only way that we're ever going to get sustainable non-fossil fuel energy in the short term. Long term, we're going to need to figure out hydrogen cell technology. Fusion is a potential. Yes, still a potential right now, not something tangible yet. But hydrogen cell technology is it's right there. We know how to make it happen. We just need to invent the engineering technology to make it more efficient.
So basically, anything that can be turned into a bomb can be used for energy.
Well, what is a bomb? It's an expensive energy, right? Napalm, C4, it's all potential energy bound up in a molecular structure that you apply an electric charge to or some other minor force like that, and it'll expend all that energy at once. Same concepts as a battery. You can make a battery and it contains energy. You charge that thing and it releases energy slowly over time, or you can release it all at once in the form of C4. Both of them are chemical reactions, right? And it's just the way that you apply the engineering to the matter. And honestly, this is where engineers come in, right? Scientists will come up with all the theories that we want. We will demonstrate that they happen, that they are realistic in a lab setting, and then we turn the idea over to engineers to bring it to life, right? That's what engineers are for. They take a theory and they make it come to life. So what's that thing? Yeah, anytime someone says, hey, this is a really cool idea and we've demonstrated that it can work in a lab, I'm just like, great, let the engineers handle it now, right? It's just like, that's literally the essential next step. So we know that hydrogen cell energy works. We just need to make it more efficient. That's an engineering problem now. We know theoretically that fusion technology can work, but we don't have the materials to make it work yet. Once we can demonstrate, hopefully by the time we get to the moon, we can get some of those rare resources that the moon has, and we don't. Once we can demonstrate that that can work, then it's an engineering problem to make it scalable, something that's efficient to work for the human population. Because right now, we can build a fusion reactor for $1 billion, but it'll only return, $1 million worth of energy in any quantity because of the limited resources we have to get it started, right? Yeah. But as far as widespread nuclear, which is your original question, that's hopefully going to happen in the next 20 years or so, where people start to trust it a little bit more. Because portable nuclear generators is really the only way we'll get any sort of long-term energy on the moon or on Mars or anything like that. Solar has very little return. Solar panels reflect most of the light that interacts with them, right? They only absorb about 30% of the photons that interact with them. I wish it was the other way around, because I have solar panels on my house. I wish I could get 100% retention of those photons. Man, I'd be making some good money off of that. Yeah.
Do you think they could like just change the, like I was thinking about this the other day, do you think like changing the shape of how, I don't know exactly how they work, but like, there's gotta be a way to like make them more efficient.
Of solar panels? Changing the shape of solar panels, people play with that idea all the time. The reason why they've settled on the rectangular shape, for the most part, is the actual photovoltaic cells that are inside of the panels. They can nest them together in that shape, and a rectangle is a very easily replicatable, placeable shape, right? You can interlock them very easily together. The other cool design that's been going on are photovoltaic shingles for houses, where each individual shingle is its own solar panel. So you can cover the entire roof, and at any time of day, you are receiving a lot of sunlight. Those are extremely efficient, but extremely expensive. Think about how many shingles are on your roof, right? And then what happens in the next hailstorm, right? How many times do you have to replace a roof because of a terrible hailstorm around here? It happens all the time, right? So there are still problems, and again, they come down to engineering problems for making something like that work. But yeah, there are so many ways we can make clean energy. It's just a matter of making them more efficient. But yeah, nuclear is by far has the most potential for short-term return on that. Long-term, until to an extent, because eventually, like the amount of nuclear fuel that we can generate, it's difficult to generate it, right? Because you have to get some ore, and then either it's naturally radioactive or you have to force it to be radioactive. You can instigate an unstable reaction. Okay, you can turn uranium-238 into uranium-236 for a reactor, but that takes energy to do it. And is the juice worth the squeeze on that? When you take into account the energy to make it the ore, and then build your reactor, and then function your reactor, do you get more energy out in the long run than it takes to make that happen? These are all the questions you need to ask, and this is what fourth-generation reactors are supposed to be improving on.
Isn't it also like kind of like most like a one-time investment because don't they last like 20 years or something like that?
Nuclear reactors can last up to 60 years now, and that's mostly because of infrastructure dating, right? Like none of the reactors in the first-generation reactors are safe. The second ones, I wouldn't even call that. The most recent ones, those third-generation ones, I want to say there's like 600 of those, are only 20 to 30 years old, and they are already severely out of date technology-wise. And it's extremely hard to update their technology because shutting down a nuclear reaction is risky. The only way that we can really do it is you build these, essentially it's like a honeycomb, like in a beehive, where each rod of uranium that is producing the energy, you pull that down into this honeycomb cell, which is made of graphite. Graphite absorbs the neutrons happening from your nuclear reaction, which are causing all of this radiation in the first place, okay, heating up the water or whatever other your coolant is around it, making that steam. The graphite absorbs that radiation and stops the chain reaction from happening. Okay, all well and good, but if you do that for too long, when you pull up your fuel rods again, you'll need to infuse it with a bunch more energy to get the reaction going up to where it needs to be to warm up your reactor again. So there's a lot that goes into shutting down a reactor and updating it and then starting it again. And what exactly systems do you update? And how do you go in there to update it, right? There's a whole bunch of factors that go into that. So it's actually cheaper in the long run to shut down an old reactor, decommission it, and build a whole new one than it is to try and take an old reactor and fill it with new technology. That's what it comes down to. Yeah. Great. All right. So now that we've talked about matter and atoms and such, let's refresh our memory on a mineral. If you don't have your notes from 1403, then allow me to remind you on the definition of a mineral. A mineral is any naturally occurring inorganic solid that possesses an orderly crystalline structure and can be represented by a chemical formula, right? And as you remember from the exams in 1403, it was pretty essential for you to remember that word for word. I didn't ask you to memorize it. I just needed you to write it down, right? Memorization is not required in my class, right? It used to be when I took this class back a decade and a half ago. I had to memorize a whole ton of stuff. But you guys aren't going into geology unless any of you have changed your majors and neglected to tell me. Did any of you change your majors to geology? No? Okay. Shucks. All right. That's all right. Doesn't matter to me. Okay, this is that definition, okay? Now, the difference between a rock and a mineral was something I really pushed home. Can someone remind me what the definition, or not the definition, what the difference between a rock and a mineral is? A rock is made out of minerals. And a mineral is not a rock. What's my favorite example for explaining this? What's my favorite example for pretty much anything? Food. Chloe knows me so well. In particular, I love using cookies to explain this one, right? You guys remember my chocolate chip cookie example? Yeah. Okay. Huh? So fast. She's like, yes, I remember all the cookies you keep bringing up. Okay. Yeah, so in the same way, a single chocolate chip is not a chocolate chip cookie, a mineral is not a rock, right? It's part of a rock. And all minerals have properties. You guys remember all these properties fondly, right? This was a good experience for you. Yes, okay, so you have your optical properties, like how your light interacts with it, things like your luster. And then you have things like your shape. Then there's the strength, your Mohs scale of hardness, where I gave you that plate of glass and you had to scratch your sample on it, right? Oh, yes, this is evanescence, by the way. You guys know why this is up here? Okay. You guys remember the word I taught you, effervescence? Yes. Okay, maybe you see where this is going. At least a few times a term, I will have a student submit a piece of work where they meant to say effervescence, but their computer or their phone or whatever they submitted it on auto-corrected that word to evanescence. And so they'll be describing a mineral and be like, observed strong evanescence on this sample. It's like, oh, you were listening to dark grungy music, were you? Right? It's just like, it's wrong, right? So always spell check. That's why I have this up here. Your computer or your phone will probably try to auto-correct it for you, okay? So this is actually effervescence, okay? Right there. Okay, that's what happens when you put hydrochloric acid on a sample and it bubbles and it has that effect, okay? Chemical reaction, by the way, it's releasing a gas. That hydrochloric acid is bonding with the calcite in this sample and it's releasing carbon dioxide. Mostly carbon dioxide is a gas. Okay. All right, so just a quick recap on these properties. Your luster is the way that the light interacts with the outer surface of your mineral, okay? So you would describe it with things like glassy, metallic, oily, earthy, things like that, okay? Then you've got your light transmission, how much light goes through your sample, right? Remember, you turn your phone upside down, turn on the flashlight, and you put your sample on top of it. Opaque, no light goes through it. Translucent, light but no image. Transparent, light and an image, like glass in our windows, okay? Then there's the color. Color was tricky, though. How many of you got sidetracked or tricked by the color on your samples? Yes, it's very easy to let that color because it's the first thing you notice. But that was part of the exercise, was teaching you to look at the other things, not just the color, because the color will trick your eyes. Then there's streak, when you would take your mineral and you scratch it on a white or black porcelain plate. That gives you a molecule-thick layer, or a few molecules thick layer of that sample, so you can actually see what its actual color is against a different surface there. So like how this one looks goldish, but is actually black on the plate. All right, and then there's all the different shapes we learned about. There was that website I gave you with dozens of different shapes, right? Here's just a few examples of those. Tenacity. This was the tough one for a lot of you because I couldn't actually give you a hammer and ask you to break a sample, right? Wish I had that kind of money to throw around, but I don't, okay? So tenacity is the way that a mineral breaks under pressure, okay? So it would be either brittle, which means that it shatters, malleable, which means that you can force it to bend and it will retain that shape, elastic, which means that you could bend it and then release it and it would snap back to its original shape, sectile, so it breaks into shavings, like a piece of wood when you break it along the grain structure, okay? Those are some examples right there, okay? Then there's the hardness, right? I give you guys the glass plates to scratch them on. Cleavage, oh man, cleavage. Great memories of trying to figure out mineral cleavage, right? Cleavage is the way that your mineral breaks according to its internal atomic structure, okay? So if I have bonds that are weaker in one direction on my atomic structure and bonds that are stronger in another direction, it's going to break along the weak bonds first, and therefore I'm going to get a flat surface in the direction of that breakage, okay? That's your cleavage, all right? When it doesn't have cleavage, it has fracture. So it'll break kind of randomly in different directions because bonds are all equally strong in every direction. Density was not something that we measured, but it's very relevant to our conversations that we had, right? Density is a measure of mass per unit volume. So the more volume you have while you maintain the same mass, the less dense your material is. If you maintain the same mass but decrease your volume, you increase the density, and therefore your object is more likely to sink in whatever you put it in. Specific gravity isn't really important. That's not something we particularly discussed. Taste, same rules apply, where I'm not having you identify any minerals. So if this is like bringing back some trauma to the front of your mind, please breathe. No mineral identification here today. Your lab does have a few pictures that I want you to try and identify, but there are no samples associated with it, and I do give you properties to help, okay? But if you ever do go back to those samples at the back of the room that we used in 1403 for any reason, reference or whatever, please make sure you are still respectful of the rules I made, 18 and 37. Wash your hands after and do not taste them, okay? There's textures that are unique. There are smells that are unique. There's magnetism. Some of your samples are going to be magnetic, right? We learned about magnetite. We learned about iron, which, by the way, is another fantastic way of figuring out if you're looking at iron. It is magnetic. Iron is commonly magnetic, okay? And then there's the effervescence with calcite. Speaking of iron and magnetism, last year I got 3 different calls, and this year so far I have gotten 1 call asking me to go out to different locations around town and identify whether or not a meteorite had struck. And I did find a few. I went out to the airport last year, back in October, and they said, hey, we think a meteorite hit one of our tarmacs last night. Could you come out and take a look? Went out there. Yeah, it was a meteorite impact hit the night before. Couldn't find any of the pieces, though. So either it was a stony meteorite, which means I wouldn't be able to find the pieces and all the rock, or it was an iron meteorite, but its pieces got blasted in tiny little bits and I couldn't find them in the grass. So to help solve this problem, I ordered some rare earth neodymium magnets. And one of my projects before summer, I'm hoping to get to it, is I'm basically going to build a meteorite finder. So I'm taking a plate of 1/4-inch acrylic. I'm going to do this at the Fab Lab. And so I'm going to take a plate of acrylic and I'm going to carve I'm going to laser cut some sockets in it. I'm going to put the neodymium magnets in there. I got about 100 of them. I'm going to place it around there, big old sheet of acrylic, okay? And then I'm going to attach that to an angle arm, which I can strap to my arm. So I can it'll look like kind of like a metal detector, but I'm going to make it for like 20 bucks, right? I'm just going to walk around, and because rare earth magnets are extremely strong, they're going to pull any pieces of metal out of the grass or rock and up onto the plate. And then I'll be able to pull it up and see, oh, yep, there's a meteorite fragment, there's a meteorite fragment, there's a meteorite fragment. It'd be way easier than spending 2 hours at the airport bent over like this, picking through the grass.
So it's like you know it's around them?
Mm-hmm.
So I know what?
You know it's around them?
Yeah, because it was a meteorite impact in the airport tarmac. So, you know, the tarmac where the planes pull up and land and where they take off from, there was a hole. It was a blasted hole right there and little pockmarks around it, which is very characteristic. Normally, when a meteorite is coming down through the atmosphere, it will break apart a little bit, either through melting or through the pressure and heat of passing through the atmosphere. And so you'll get one major impact and then tiny little impacts around it. It was absolutely that. yeah, the asphalt on the tarmac had gotten blasted apart and melted by the impact. So the only thing I couldn't find to prove that it was the pieces of the meteorite. But by looking at the impact, I was absolutely satisfied it was an impact.
Was this like on Halloween? Because I remember seeing
No, this was actually early October. Yeah, early to mid-October. It was before Halloween, I know that for sure. But there have been a few other sightings since then. So if you saw one on Halloween, I absolutely believe that you did. Yep. I've seen 2 pretty big shooting stars just this year, just by looking up. So we're actually passing through, I believe, I read this somewhere. I think it was on a Planetary Society newsletter. I think we'd be passing through, our planet is passing through a debris field at the moment, which is why we're seeing so many meteorites. We'll come and go through those all the time. Because our planet is orbiting the sun. Our sun, and therefore our solar system, is orbiting through our galaxy. So our planet will pass through local asteroid fields or local debris fields out in space in our solar system. And our solar system will encounter things as we go through the galaxy. So every now and then, something will just randomly pass by. It's pretty cool, yeah. Yeah?
When I do my national photography stuff too, when I go through some of the single frames, I can see like shooting stars.
Yeah? Oh yeah, that's awesome. Right now I'm saving up for a C-Star S30 Pro telescope. So excited to put that puppy to work. Leave it out overnight and then see pictures of galaxies. Oh, it's so cool. Okay, let's talk about minerals. Our minerals are grouped into a couple categories. We have silicates and non-silicates. Silicates are the ones that form through the igneous process, where you get silicon tetrahedrons that form first in your magma. And then different metals will latch onto those and make structures based on cooling, right? This is where Bowen's reaction series comes in. You get different minerals that will cool and form at different temperatures, right? So you remember we start with things like the olivine and the pyroxene and the amphibole and move on into our calcium feldspars and then our potassium feldspars and our biotite micas and our muscovite micas and then our quartz right there at the end and all of that going down through Bowen's reaction series, right? But all based around the silicon tetrahedron. That's what makes your silicate minerals. Then you get non-silicates, which are everything else. Non-silicates only make up about 8% of the Earth's crust. The other 92%, silicate minerals, okay? Yeah, so 8% of the Earth's crust, non-silicates. This includes all of these things, which we often will use as valuable Earth resources, okay? So we'll have things like, yes, ice, okay? Things like calcite, gold, copper. All of those are non-silicates because they make their crystalline structures, they are minerals, but they make their structures around other things besides the silicon tetrahedron. Our 3 types of rocks are igneous, metamorphic, and sedimentary. Igneous rocks are the ones that form from cooling magma and lava. Remember, it is lava if it's near or on the Earth's surface. It is magma if it is under the surface. Okay? So magma that cools off underground, we will call that an intrusive igneous rock. Why? It's in the ground, right? Intrusive igneous rocks are ones that form from magma that cooled off underground. Extrusive igneous rocks are ones that formed from lava on the ground, on the surface. Okay? The compositions depend on this ratio between silicon, free silicons in my magma or lava, or I should say, iron and magnesium. Because if I have a high quantity of iron and magnesium, I'm going to have low silicon. There's that inverse relationship, right? The more iron and magnesium I have, the more mafic my composition. The less iron and magnesium, and therefore more silicon I have, the more felsic my composition. And remember, it is the silica in my melt that determines the viscosity. So more mafic magma with less silicon is going to be runnier, less viscous. More mafic or more felsic magma with more silicon and less iron and magnesium is going to be less runny, thicker, more viscous. Okay? Then you have intermediate, which is a cross between the two. It's going to land somewhere between mafic and felsic in composition. Then ultramafic, which is going to be your super dark, way deep underground, mantle-type rocks like this one right here. Piece fell off. Full of olivines and pyroxenes. Just the super high temperature, high pressure, deep underground minerals that form there. Okay? That's going to be your ultramafic composition. As always, feel free to stop me at any time if you have questions about something. All right, now I'm just kind of skipping through, refreshing everyone's memory on this. Then we have sedimentary rocks. Sedimentary rocks are separated into a couple of different categories. You've got your detrital or clastic sedimentary rocks, which are made from the broken pieces, the weathered, physically, mechanically weathered pieces of previously existing rocks, and they get compacted together, and you make that clastic sedimentary rock, also called detrital. Then you have chemical sedimentary rocks, which are made from the reprecipitated, chemically weathered or dissolved remains of other rocks. Okay, so if I dissolve a rock in water and then evaporate that water, it's going to leave the dissolved pieces behind and make a new mineral out of it. That would be an example of a chemical sedimentary rock. Then you have organic sedimentary rocks, which I've separated out from chemical sedimentary rocks for this class because we spend a substantial amount of time talking about the things that make organic sedimentary rocks in historical geology. So we're going to discuss them in a separate sort of category for this class where I combined them with the chemical or bioorganic ones before. Okay? And the organic ones, those are made from the remnants, what's left over from formerly living things. Like coal, for example, is an organic sedimentary rock. How do we tell the clastic sedimentary rocks apart from each other? Well, there's those characteristics we learned like particle size, grain roundness, and sorting. All of these give us indicators for the environment that sediment was deposited in. Grain size tells us a lot about the energy of the water or wind that was present at that time. Why? Why would grain size give us an idea of the energy?
High energy, smaller.
Right now, can you lift a 50-pound bag of concrete? What if you spent every day for the next 6 months practicing your weights, weight training? Would you be able to pick one up then? Yeah. You put more energy into something and you can pick up a larger thing, right? Yeah, okay. So my stream that has high energy will be able to pick up larger particles, okay? Smaller energy can only pick up smaller particles, okay? So by looking at the grain size in my sedimentary rock, I can determine approximately how much energy was present at the time that it was deposited at that location. Okay? Then there's sorting. That's how many of the particles in my rock are approximately the same size. Are they all medium grained, or is there a mix between fine, medium, and large grains? What does that tell us? If I have a rock that is made from fine, medium, or large grains, okay, all of them mixed up together, what does that tell me about the depositing environment? High what?
High energy because it's able to carry high rocks and then the medium rocks and the small rocks.
It was able to carry all of them. So you're right, that means it had high energy, but then what happened?
It went back to low.
How fast? Fast. Why do I know that happened fast? Why do I know energy was lost quickly? Because it didn't drop out the large ones, and then the medium ones, and then the small ones, like what would happen if I lost energy slowly. It dropped all of the particles out at the same time. So I went from high energy to low or no energy like that. And that's why all of those grains are mixed up with each other. Good. Interpretation. You guys are figuring out how to interpret rocks already. Look at you. Okay? What about the shape? The shape of the grains in my rock. If they're more rounded or less rounded, what would that tell me?
Less rounded, less energy, more rounded, more
Potentially energy, but more broadly speaking.
more weathered.
Exactly. Why is it rounded in the first place? Weathering. Remember, weathering removes corners off of things before everything else. More surface area on corners. So if I have a rock made from, a classic sedimentary rock made from rounded grains, that tells me that that sediment got weathered more before it got turned into a rock. Probably means it came from further away. There was more time for it to get weathered as it got transported. Okay? Okay. Then you have your chemical sedimentary rocks. Okay? So you've got stuff that forms via evaporation. Okay? Like salt, gypsum, travertine is an example of this. Travertine is a type of limestone. All of these form as minerals that have been dissolved in water reprecipitate as the water evaporates away, because you can't evaporate salt, gypsum, calcite, any of this stuff into the sky. It doesn't go. Only the water goes, leaving behind whatever was left. Okay, whatever else was in there. And as the concentration of that dissolved stuff in the water gets higher, the amount of water decreases, enriching the concentration of the other stuff. It eventually starts to form the crystals of that stuff again. Like if you were to mix a whole bunch of, maybe this has happened to you. Have you ever made like a really, really like strong lemonade and then forgot to drink it? No? Maybe I only know this because I have kids. One day, some of you will have a child that dumps half a container of lemonade in their cup of water and then takes one drink and goes, and then hands it to you, and you're like, what were you thinking? And then you just put it on the counter, and you come back to the next day, and there's going to be crystals of lemonade at the bottom of that thing. It won't have all dissolved anymore because some of the water's gone through evaporation. And so the crystals are reforming at the bottom of your glass. Okay? Biochemical, this is what happens when organisms take in that dissolved stuff in the water, make their shells, skeletons, assorted other body parts out of it, and then those animals die, and those body parts are incorporated into the rock at the bottom of the ocean. That's biochemical. And then coal is similar, where you have the body parts of living things, usually trees, algae, mosses, bushes, grasses, things like that. And then they get incorporated into sediment in an anoxic environment. What does anoxic mean? No oxygen. Yeah. Oxic means oxygen present. Anoxic, no oxygen present. Why would that make a difference? Because oxygen does this annoying little thing called oxidizing. Okay? You're very familiar with it. Fire is oxidation. Rust is oxidation. Oxygen is affecting you right now. Oxygen actually oxidizes your cells, your DNA, breaks it down eventually over time. This is why aging occurs. Your body starts to break down. It can't keep up with the constant process of refreshing itself against the forces of nature that we live in, including the presence of oxygen. Your body eventually gets oxidized to the point where it can't sustain itself anymore. Okay? It plays this role in breaking down cellular structures. So, if you're in an environment without oxygen, stuff doesn't get broke down. It gets preserved, and it gets buried deeper and deeper, mixed in with dirt and water and all that stuff. And as it gets buried deeper, it starts getting cooked. Increasing temperature the deeper you go underground. Remember that? Increased pressure, increased temperature, you start cooking your biomass, and you start forming coal. This is how coal forms, okay? One phase after another, you get coal, okay? So we can take all that information that we now know through sedimentary rock, okay, which are processes that occur at the surface, and igneous rock, which are processes that occur underground, and you can make a pretty solid picture of what goes on in both cases. And we can make some very apt interpretations of Earth's history. But that's not it. Those are not the only two types of rocks. There's one more type of rock. What have we not hit yet? Metamorphic rock. Metamorphic rock happens when you get application of heat and pressure to the point where your minerals do not melt, but they do experience a physical and chemical change, okay? Your heat is going to allow your ions to mobilize and change their configuration, making larger minerals usually. Different minerals as well, but larger minerals as well, okay? And then and that heat can come from a couple of different sources, right? We've talked about this before. Your heat can come from rising magma, burial over time, tectonic plate interactions. You can get this heat a couple of different ways, but when you combine that with the pressure that you get underground, you get metamorphism. That heat plus pressure is going to cause your rocks to change physically and chemically into a new type of rock. Metamorphic rock specifically, okay? The two types of pressure will help determine which type of metamorphic rock it's going to be. So normal pressure at depth is called confining pressure, okay? That's equal pressure from any given direction. That's going to make metamorphic rock that doesn't have any particular mineral orientation. They're just going to remineralize themselves into larger structures and not in any particular way. In the way that marble doesn't have any linear association of minerals, but they're all calcite just like the limestone that it came from, okay? Differential stress, though, that's the one that causes unequal forces of stress in any direction. And what do we remember about that? If I apply unequal forces of stress to this paper, what does it do? It folds, and so my layers of rock are going to fold up or down a lot of the time, while my minerals in those layers of rock are going to reorient themselves according to that direction of stress. And in what direction do they reorient themselves? Huh? Does it always have to be up or down? Perpendicular to what? To each other. Though it will end up being parallel to each other, which is perpendicular to what, though? The stress applied. Yeah. So if I apply stress this way, my minerals are going to reorient themselves to be perpendicular to that stress, which in this case is up and down like what you're saying. But what if my stress is being applied this way? Yeah, they'll be going this way, which isn't up and down. So you had the idea. Just think of it in terms of, 3 dimensions instead of just the example I gave. But that's good. That's good. Okay, yeah, perpendicular to the direction of applied stress. Great. Okay, that's called foliation, that planar arrangement of minerals. And you can get that a couple of different ways. You can get minerals that get squished flat. You can get minerals that remineralize into the new direction, whatever that is, okay, as a product of that force applied. Or you can get them that they go, whoop, just change. So you get recrystallization, reorientation, and squishing, flattening. Okay? Those are the 3 ways that you can get foliation of your minerals. So my layers of rock could be doing this as a response to that stress. And the minerals in those layers of rock could be going perpendicular, not even following the trend of that body of rock anymore. This is what makes metamorphic rocks stand out so different. They take on a completely new texture, rock texture, unique to that particular classification of rock. One could argue that without that, you would just have a different type of mildly altered igneous rock or sedimentary rock. But it is the substantial change that you get in the physical and chemical response of the minerals to that layering, or to that stress, that changes their orientation. That's a huge component of making metamorphic rocks. And then there's mineral resources to touch on real quick. Mineral resources come from every type of rock, okay? We get oil and water from sedimentary rocks, for example. We get gold and silver and platinum. We get those from a lot of igneous rocks, or igneous sources, I should say. We find them a lot in sedimentary rocks, but they are often igneous sourced, at least in the experience I've had, okay? You can have garnets and other precious gemstones that form in metamorphic rocks. Okay? And all of these resources our civilization, our society relies upon. So understanding where they come from, how they form, these are fundamental components of how geology and society intersect with each other. And the availability of those resources as well is very important. Right now, gas prices are rising. Why? Are we running out of oil? No. Why are gas prices rising? Why is gas $9 a gallon in some places in California? Normally, that's true. 20% of the world's oil goes through the Strait of Hormuz. And right now, the Strait of Hormuz is covered in underwater mines to keep ships from coming in. Now, Iran is shooting back however they can, and that includes shutting down the Strait of Hormuz as best they could. So right now, it's a contested zone. There's a war going on over there to try and reopen it so that that oil can flow again. But since 20% of the world's oil goes through there, it's having to find other places around, and they are finding other ways of transporting it. It just takes a while for it to go the non-typical way. So gas prices are rising. Okay? They're hitting us a lot less than they're hitting other places. California is feeling it harder because they don't have the refineries. We have them here. They're local, right? Gas prices in Galveston haven't even changed, I would wager. Probably not much, right? But the further you get away from those places, the tougher it gets. So think about the nations that don't have any oil refining whatsoever, right? They're getting hit the hardest, I would imagine, okay? So being aware of where these resources come from and the sort of things that can affect them, natural and societal based, is very important, okay? Any questions about today's lecture? Pretty straightforward. You guys demonstrated very well to me that you remembered the content matter. You answered all my questions, and you had some very, very interesting ones of your own. Okay, let's talk about your first lab then, huh? Will you zoom out now? No? You don't want to zoom out? I know you can zoom out. Okay, what if you follow me first and then zoom out? I think the mirror image of it behind me is confusing it. Okay. All right. All right, so lab 1 is more or less a review lab. Okay, you start getting new stuff starting in lab 2. But lab 1, we're just going over sedimentary rocks and structures. I'm just going to breeze through most of this stuff, okay? So just a quick refresher. This whole PowerPoint here is just a refresher on some of the more common rocks and structures that we learned about, okay? Talking about the different superficial processes that go into making sedimentary rocks, your weathering and everything. Talking about some of the more common sedimentary rocks that you'll encounter. There's the shale, sandstone, conglomerate, etc. The more common chemical sedimentary rocks you'll run into and their characteristics, right? That's all in here. Some of the stuff was even in the lecture. Quick refresher on sedimentary structures, which you will see in this lab, and which we've talked about, and in particular how we can use them for interpretation, right? So things like bedding planes, which represent the changes from one layer of rock to another. Cross-bedding or cross-stratification is another way to express that, okay? Which you can see when layers of sediment are deposited on each other at an angle, and then there's some sort of change in that angle that they're deposited in. Very common with things like dunes and in underwater settings, okay? Let's see, ripple marks, mud cracks, those are all pretty self-explanatory. These are, I taught you about ripple marks, but now let me tell you about the two different types of ripple marks, okay? There's asymmetrical ripples and symmetrical ripples. Ripples form through what process? Moving fluid, okay? Water or wind, whatever the case may be. But yes, there has to be some sort of movement which is causing a shift in the sediment that's under the influence of that medium, that water or wind. So right here, I have asymmetrical ripples. These form with a very smooth, gradual slope on one side and then a steep slope on the other, or a short, steep slope on that side. Whereas symmetrical is evenly sloped on both sides. What would make that happen? What's coming from both directions? Yeah, whatever the fluid is that's moving it. Symmetrical ripples are even on both sides, symmetrical, because the water, let's call it water in this case, is going this way, and then that way, and then this way, and then that way. Can you think of an environment where we might see water going this way and then that way? Yeah, it's a beach. I can look at a symmetrical environment and think, it's probably some sort of beach setting. The water is moving in and out, smoothing both sides of this ripple to approximately the same angle. What about an asymmetrical ripple where I have direction this way? What sort of environment could I interpret water only moving one direction? Huh? Oh, like a flood sort of situation? Sure, sure. A river, yes, yes. Rivers don't flow upstream, right? They only flow downstream, only in one direction. So anywhere you have water or wind flowing only one direction, you'll get asymmetrical ripples. And so by looking at a ripple and determining whether it's asymmetrical or symmetrical, you can interpret a lot about the environment that formed it. That includes if it's been turned to rock. Okay? Burrows and tracks. These are a type of structure which we call trace fossils. Trace fossils are different from fossil fossils because they are not a piece of or a remnant of the life itself, but evidence that that life was there. A track is not a piece of the dinosaur, right? In the same way that your jacket is not a piece of you. But if you left your jacket here, and I knew it was your jacket, I would know you were here. Same way with the tracks, okay?
What's that swirly?
Huh?
What's that swirly?
The swirly thing? Oh, that's a burrow. So yeah, some rodent burrowed into the ground, making this kind of curlicue way, and they do this. Rodents do this fairly often. Think of it as a stairway that they use to get out. Okay, they do that on purpose. It's much more stable that way than a straight hole down, and they can climb up it like a spiral staircase, right? And then down here was their actual living chamber where they lived. Okay, this is an example of a rodent. Looks very multituberculate, actually, which we'll talk about those later in the class. Carving out a burrow for itself. These are actual fossils. Okay, so fossils can include bones. They can include shells. They can include trees and other plant parts, leaves, stems, etc. These are some other fossils here. These are called stromatolites. We will learn a lot about stromatolites in this class. Stromatolites are awesome. Stromatolites are the oldest fossils we have on Earth. Yeah, 3.5 billion-year-old fossils we've got of these things. Pretty cool. But essentially, a stromatolite is it is a colony of algae that, because they are photosynthetic, they want to live near the surface of the water, where they can still be in the water, but have sunlight for photosynthesis. Okay. So when the tide comes in, okay, it will bring with it a very fine layer of sand and silt, and it'll wash that on top of the algae. The algae grows up over the silt so it can access the sun again, and then the tide goes out and comes back in and brings another layer. So what happens is you get this built-up mound of algae sediment, algae sediment, algae sediment, algae sediment, and it will often turn into this kind of mushroom-looking sort of shape. These are living stromatolites in Shark Bay, Australia. This is what they look like. This is what they've looked like for billions of years. Okay? Tide comes in, tide goes out, stromatolites continue on living. Okay? This is what they look like in a fossil when you weather away the top part. Think of this as kind of like a cross-section. You know how when you take a tree and you slice it, you can see the tree rings? This is what happened to a stromatolite when you slice off the top or weather away the top, you can see the rings of algae growth from the inside out. Okay, so those are fossils as well. Now, something that it is very easy to confuse with stromatolites are iron concretions. Iron concretions are, it's basically when your water, your groundwater is filled, it's got iron sulfides, iron hydroxides, any iron oxide that will collect around some object and build sort of iron shells around it, okay? And they will end up looking like this, which sometimes confuses people into thinking they're stromatolites. They are not, okay? They are generally globby. They don't usually have that sort of mushroomy shape. They're kind of globier. They look far more like fossilized poop to me than stromatolites, but you know, it's coprolites is what we would call those. But yes, this is usually there's some nucleus, some center to these things that the iron formed around. Sometimes it is a little fossil. Sometimes it's a little rock that was caught in the sandstone or wherever this formed in. But this is an iron concretion. It happens when you have a lot of iron in your groundwater and it builds up around stuff. Okay, so your lab is going to be identifying common sedimentary rocks and structures that we have encountered in 1403 and which will be relevant for our future discussions in 1404. Very basic, very straightforward. There will be in some of the labs in this class kind of a grid system that you'll need to fill in with columns and rows. And you'll just need to put X's in the corresponding boxes where those things line up with each other. Very straightforward. Let me go ahead and actually, I wonder, here, let me turn this off for a second because I don't want to accidentally show you the answers, however much you wish I would. Let me open up the exercise real quick so that I can show you what we're looking at. Let's do student preview. Okay. So this is what you're looking at with your lab. All right, so stuff like this. Sedimentary rock is clastic with grain size between 1/16 and 2 millimeters. What's the rock name? I give you the properties. You just need to try and remember what classification of rock that would fit into, right? So there's a couple of things like that where we're trying to refresh your memory on that. What is the sedimentary structure is this, right? Pretty straightforward, very easy. Down here, which of the structures we've discussed could be useful in determining a paleocurrent direction, right? We talked about that stuff today. So just very straightforward, and then this is kind of a drop down. Match the structure to the environments they may be found in, right? And then you just click that and you click on whichever one. I will say, you'll notice that occasionally I need to have the same option on here twice for some of these. I don't remember exactly which one it is. It might not even be this particular lab, but in the future there will be ones where on drop-downs like this, I need to have the same option on there twice, but one letter will be capitalized on one and not on the other. That's because Blackboard is stupid. It doesn't let me put the same answer for two options. So if both laminations and asymmetrical ripples could theoretically be found in the same environment, it won't let me put the same answer for both of those. So I have to put a different submission with the same answer with one capitalized letter so that I can have you guys pick. But whichever one you pick, it would be the right answer. That's the dumb thing. It's like, you would think that's an easy fix, but it takes them forever to do anything with this program. Anyways, so that's your lab. Any questions? No? Clear as mud? Great. Well, I'm going to end the recording here, and we can begin lab time.